Hello! I always love coming back here. My career as a speaker started at this very conference in 2018. It was the year that they constructed the second building, and we were actually giving talks in the unheated parking garage. People were sitting under blankets for my first talk here. In the meanwhile, I've done this probably like 100 times, so I'm no longer this just starting speaker, but I love coming back to this event because, well, I have a connection with it. So, hello, who am I? I'm Hannes. I have 3 kids and a fiance. No, this is not my second fiance. It is the mother of those 3 children. We just waited to get engaged for a very long time. In my day job, I work at a company called Access in the role of principal consultant. That role basically means I do whatever the fuck I want. And I can highly recommend that as a job description. It's pretty awesome to do that. And I've been writing .NET backend code professionally since I graduated in 2005. And because I love doing this a lot, like talking to people and sharing my experience, there are a couple of organizations that have recognized that in their community program. All these titles mean is Hannes loves talking to people, okay? There's another thing. And for those of you who have not heard, tomorrow night after the conference, we will play in a bar just across the river. It's like 5 minutes walk from here. We will ruin some of your favorite songs. The entrance is free. And we will also have a little bit of free beer, like 200 liters-ish. So if you want to show up, please come and join us. We want to make it a big party tomorrow, okay? So allows no mai, doors open at 7, we play at 8. Cool, let's get to business, databases. When I was writing this talk, and when I was thinking, what are the most used database engines today? And luckily, there's a way that we can find that out. The people of Redgate have this website called dbengines.com, and on dbengines.com you can find a list of the most used database engines. They base this on Google searches, Stack Overflow issues, statistics and telemetry, like they base it on a whole bunch of things. And according to them, these are the most used database engines at the moment. And what we see there is a trend. 5 out of the top 10 are still relational databases. I know that Snowflake says relational, but like different beast. But all of these are just like ACID-compliant relational databases. And I don't know how it is with the college curriculum here in Lithuania, but in Belgium we are still teaching young developers to just normalize their database and use SQL databases. But if we go and look at where these ideas come from, it was first called SQL, like written out, a structured English query language. So a domain-specific language for querying data. Anybody care to guess when this specification was invented? 74, yes, 70s, good guess, right? And it took a while before it became an ANSI standard, because that transformed into an ANSI standard, and this ANSI standard was 1986. Now, from that time to now, a lot has changed. So if we look at how the standard evolved, we had SQL 86 and SQL 89. Notice some peculiarities. In 86, we could create tables, but we couldn't alter or drop tables until we had the 92 standard, right? So for all those years, you cannot change your database. You could add tables, right? This is just a standard. Every database engine had their own ways of doing this, but it made it into standards. Like a lot of the stuff that we use today was already there, like early 90s. After that, it was basically very minor changes that do not dramatically change the way that we use database engine. This is important because this is a time spirit that was different from what we're living in today. Because what we are taught when we are using these relational databases is to normalize your data. If you have a bunch of data points and you want to organize them properly into a relational database, what you're going to do is to make sure that every little bit of information gets stored in a single field, in a single row, in a single column, in a single table, right? And that's the whole point, because then we can get consistent data across all of our data models. Now, there's some other stuff that was in the time spirit of when these standards came. If we look at mid-80s and we look at the price of a hard drive, I found this ad from the 80s, and $3,400 for a 10 megabyte hard drive, 10 megabytes, right? And if we adjust that for inflation, that's 12K today, right? Imagine that the hard drive you're connecting to your desktop is 12K. That's a lot of money, right? Now, what does 10 megabytes get us? If we listen to music, how much music can we listen to on Spotify for 10 megabytes? Like 5 minutes, right? If we watch Netflix in 4K, yeah, I see you laughing already. 5 seconds. If we go on the homepage of a newspaper, and I think this is really funny because some of my colleagues maintain one of the popular websites in Belgium, so I make fun of them. You can get 1/3 of the homepage because that's a 30 megabyte page load right there. I always find it fun to make fun of them for this. But that's a $36,000 homepage if you want to store it. $36,000, okay. So in this context, storing data twice, having those 10 megabytes becomes a very, very important thing, right? We live in a different time right now, but we won some stuff and we lost some stuff by using these relational databases. We won, definitely, on the data integrity side. It's very easy to keep our data completely integer by having every bit of data stored in one place, right? We can win there. We also win in consistency when we want to have those asset transactions and we want to modify our data. Getting data consistent, if it's only stored in one place, we also definitely win. So we get consistency, we win that. We also win a lot of disk space because we're storing every bit of information only once. Very important when your hard drives are 12K, right? Not as important today because, well, when is the last time you worried about disk space? In your cloud bill? It's pretty far down the line, like compute and RAM, network traffic, then maybe disk space, right? When you're building a new PC, even if you get those fast PCIe 5 SSDs, like it's not something you really worry about, right? What did we sacrifice to get that? And this is the part where I feel like in college we don't zoom in on this quite a bit. And we have all taken for granted that this is the way that we do data. And what are we sacrificing? We are sacrificing performance. Because whenever we fetch data, we are usually joining together a couple of tables. And the tricky thing about this is compute that is very hard to distribute because it's compute that runs in our database engine. And if you know how database engines are licensed, you know that that is very, very, very expensive compute, right? So we're losing performance. We have to deal with locks because we're modifying all of that data and we're locking that data when we do writes on this. We also lose history because when we overwrite a field, actually the old version of it is gone. We don't have historic data by default in a relational database. Now, what if I told you that we could sacrifice the one that we care least about on the left? Because times have changed and data has become cheap. And we can win all of those back. Wouldn't that be cool? Well, that's what I'm proposing to you today as a trade offer. That is what event sourcing is going to do for us. This will be our hero of the day. So what is event sourcing? Now, let's take a step back at what we do. If we write any kind of code, we're often going to have some kind of command that comes into a system, a request for our system to perform a certain operation. And at the end of the processing, our system will communicate that it has done something. Let's call those events. Something has happened. We're communicating that as events. Now, somewhere in the middle, we're going to have to put some code that makes that happen. That's all that does. But that code usually has to verify with the current state of our system what the results of the command are going to be. You're going to fetch some data, run some logic, maybe write some data back, right? Very typical stuff. We do this every day. Now, if we look at this through the lens of time, and this is maybe a little bit of a shortcut when I talk about this, but a command talks about what the future is going to look like. It's a future request from our system. It doesn't matter whether this comes from a button press of a user, a message that comes in over a bus, an API call. It doesn't really matter where that command comes from. At the moment when we issue it, it is a request. It still needs to happen, right? Events communicate about the past. Something has already happened. We don't have a time machine. We cannot change it anymore. It has taken place. It's merely communication. And the state, when we are processing a command, usually talks about the present. What our system state looks like today. And this is important when we start thinking about it. And then I ran into this tweet and I worked that into the abstract of this talk. And every complex system becomes a way of message passing. And it's all a matter of how far you zoom in, but at some point you're always passing messages. State is a way that we pass a message to our future system, just like we use memes to communicate to future generations, right? But we do use state to communicate to our future system, because in the future we're going to have to handle new commands and we want to communicate how we pass in that state. How about we make that a little bit more explicit over time? Because the thing that we often, this is the typical example when we talk about event sourcing and why it's important. Let's say that you're building a shopping cart for an online shopping system. I'm putting in product A, then I'm putting in product B, and then I'm browsing the site and I find product C, which is a better version of B, so I'm putting in C and I'm throwing out B again, right? Sound familiar? You shop like this, I shop like that, we all do, right? The state of our shopping cart at that time is product A and product C. We have lost very, very relevant information. The fact that we put in B first and then took it out after we added C, if we see that same behavior between those two same products over a lot of different users, we can conclude that these two products are related. And depending on what I want to push on those users on my shopping site, that is going to be very, very important information when I'm building my recommendation engine. It's not going to be important to my checkout process, but we are losing valuable business data by only storing state and by not storing the events that led up to the state. So if we model this over time, a command comes in, and that command gets processed and it raises a bunch of events, but it also makes sure that the state in our database is the state after that one command, right? If we do that again for the second command, we add some new events, because you can have more than one events from a single command, but we actually override the state with the new state. And if we do this a few times, like we've lost state A and B, we only have the final state. Now, what is important is, can we go from state and derive the events again? No, we cannot. That's always going to be very educated guesswork. We can get close, but never truly there. If we have to go from the events to the state, that's actually the easy bit, because if our events contain all the things that have changed in our system, if I have those events, product A added, product B added, product C added, product B removed, if I have those, I can derive the state of my shopping cart, right? So if we want to not lose the lossy format, we can store the events and we can always bring back the state, but not the other way around. So if we start representing this as such in our data store, that's when we start talking about event sourcing, because normally our shopping cart has a shopping cart definition with the user and whatnot, and then we add lines to the shopping cart for all the products that are in it. It's usually a couple of tables with relations between it. We can also represent all of those tables together as one shopping cart root entity, and we store for that one entity, that one shopping cart, my shopping cart, we basically add all the events in a timeline, and we store that instead. Now this is very beneficial, right? Because we have won back most of the things already. First of all, we are only appending at the end. We don't need any locks, right? Second of all, we are not losing our history. Also very beneficial, right? And we, what was the third one? I'm stuck here, okay. I'll get back to it in a second. But we have actually won all those things back by storing our data like this, but we are losing this space. This is going to have redundant information in it. It's going to take a little bit more space to store. So That is what event sourcing is. I promised you this. I get that you maybe feel like I gave you this or maybe even this. But there's more to it. There is more stuff that we can do with event sourcing. So let's dive a little bit deeper into how to deal with this in your code conceptually, right? And one of the things that you're definitely gonna have to deal with somehow, but there's frameworks that do it for you, is the way that you handle commands, because we're not storing our state anymore. We're storing events. So it's stored as events, and we have a command that comes in, and what are we gonna do? So the lifecycle that we're gonna have in our applications when we are processing commands, and remember they can come from anywhere, and we're gonna create a handler that handles that command. And that is just some code, a function in a class somewhere. And that is going to locate the entity. So far, so good. This is still the same as you used to do with an ORM and or any type of code that talks to a relational database. But now we're going to have to construct that entity by its ID. So we're going to fetch all the events from the stream. And this stream is a stream for that one entity. We're going to fetch them all, and then we're going to replay them. So we're going to call some functions that are actually processing all these events to reconstruct the state. And then we have our state, and then we can do our work. So our handler can execute, it can do its work, and the result of that handler is not writing back to the state, because we don't have the state anymore. What we're going to do is we're going to generate new events. And as soon as we have the new events, we just append them at the end of the stream, and we are done. This is the behind-the-scenes lifecycle that will happen. Most of the time, you don't have to do most of this by hand. Unless you want to roll your own framework, this is handled by a framework that does this for us. But it's very good to realize behind the scenes what is happening. Now, a question I got a couple of times when I gave this talk, the first time I gave it, is why don't we store the commands? Because the commands are at the beginning of the cycle, the events are at the end. Why don't we store the commands instead of the events? Well, there's some very good reason for that. A lot of the heavy processing happens in the handler. If we're going to have side effects, if we're going to be calling external systems, we are going to have that code process every time that we replay that command. So that's often less desirable if we get subsequent commands for the same entity, that all that stuff would replay, right? Also, the code in those handlers is much more likely to change and yield different events in the future if we process the same command again. Because the business logic changed, the events will look different. As I told you, we don't have time machines, so we don't want to change that. We want to have it as it was processed at the time. So it's impossible to manage if we would store the commands. On the other hand, in the entity, we're just going to assume that events are true, that they were correct at the time. Yeah, sorry about the music. That they were correct at the time that they were generated. And we don't have to do any checks. So a lot of this replaying events is just setting properties on an object. And that's super fast to do. You can replay a couple of thousand events in just a few milliseconds. It's not a problem at all. So that's why we store the events and not the commands. We just assume that they're true. We're going to replay them. It's going to be very fast. Also, because we're not doing joins anymore, we're taking pressure away from our database. That was the third one that I forgot to mention. We're taking away the stress from our database, and now the compute is going to be in our application level, which is going to be much easier to distribute. We can much easier have that compute of the replay happen in different nodes. So how do we store that? We basically need two things. Which stream or which entity does this event belong to? And what is the sequence number for this event? Because we need to replay events in order. If we replay them in the wrong order, we might get different results. We don't want that, right? And then we need the event data. And the event data usually is a serialized version of your event object. Then, of course, you need to deserialize it afterwards, so you're going to need to know what type it is. Often a timestamp is very useful, like when does they take place. Then we often add some metadata, correlation IDs, that sort of stuff. But don't worry about that. Like conceptually, this is like the simplest event store you can write. You can put it in a relational table if you want. It doesn't really matter. It's just going to be an append-only table. Very easy to performance tune. So it's append-only. We don't have to do any joins. And we have our full history intact. Every event that ever takes place in our system will get stored in event streams, right? What does this look like in code? Well, I'm a .NET guy, as I already mentioned. So we now have records. In these commands, you have to pay attention. There is always a locator that helps us locate what entities we need to process this. So in this case, the ticket IDs are in the commands. And then the content for whatever you need to process. For the events, we actually don't need those IDs. You can put them in if you want. Doesn't really matter. I love the fact to use records because they show as immutable. They're immutable in code, but they're also immutable over time conceptually in our application. So I love signaling that like that. We don't need those IDs because they're stored in the event stream correlated to this one entity that they have taken place for. Now, what does that entity look like? This is typical code that you will write in any language or any event sourcing framework that you will have. You have an entity that has a bunch of fields, and those fields will get filled up with having all of those events played back. And for those events that are playing back, you have those create and apply methods that just modify the state of this entity if you work in a mutable way, or do it like this, do it in an immutable way and recreate new instances of your root entity. This is the part where you're gonna do something that you didn't used to do before. Right? You didn't have these apply methods because you were updating the state directly in the database. You were doing it in a different way. But this isn't hard to reason about. The advantage of this is very side effect free. You're looking at a single apply method and you can very easily see what this type of event does to that root entity. So if you hop into a new code base, it's very easy to understand what's happening. So if you have a handler, that would look like this. And this is using a framework called Martin. We have a framework that does that whole replay. And that's what's happening on that first line. We do the fetch for writing. It's just like, hey, fetch me all the events from that entity and replay them into a ticket entity, right? Framework does that for us. That's the first three steps of our life cycle. And then we are just doing our logic. So we're seeing if the ticket already has a resolution, and then we append a new event to the stream. And then just like if you would with an ORM, you're gonna use that document session as your unit of work, basically. And that unit of work is all gonna save in one go to the database when you hit these save changes, right? This code looks very similar to what you used to write against a relational database, right? The only thing is that behind the scenes replays all those events instead. So that's not becoming harder. Now this gets mentioned in tandem with CQRS and DDD all the time. So you don't need event sourcing to do CQRS or to do DDD, and the other way around. Like these three concepts are separate concepts, but they fit together quite well. Let me explain why. So they're not the same thing. Now CQRS is, it's funny to talk about CQRS at a conference that was founded by Greg Young. You all know this, right? Yeah, so I hope I don't get it wrong. He will probably watch this talk afterwards. CQS was a concept that came before CQRS, and it was basically you should separate the writes from the reads in your system. A write should not return any results. A read should not change any state. It's just to have a clear API against what you're doing. You can put it in two separate endpoints. It doesn't really matter. But write methods should only write data and not return results. Query methods should only return data and not change anything. Now, when we start talking about CQRS, because this is command query separation, and now we are talking about command query responsibility segregation, when we use different models on the two sides, a different model to process commands and a different model to query data, that's when we start talking about CQRS. We can put those models into two different data stores if we want. They could still be in the same database, but they should be hitting different tables there. At some point, you're gonna have to bring over the results of your commands to the read side. That's the tricky bit. We can do that with SQL agent jobs. We can do that with ETL, like that's not a problem. But we found out really quickly that it's much easier if your command API spawns some events, and we use those events to project data into our read model. And that's where event sourcing starts making complete sense, because if our command API is using event sourcing as its storage model, we don't need to spawn separate events. We can just read the event stream and run projections against that event stream and project into a read model that we can then use for querying. And that's why CQRS and event sourcing fit together so well. Now I'm talking about projections and I didn't quite explain that yet. A projection is just a bit of code that subscribes to certain events in your event stream. It's not going to have it the whole stream. It's going to have some kind of filter to tell it which events it should care about. And then that projection logic is going to do create, read, update stuff on the read model database and modify that model for us. And we can store that into anything. Could be a document database, could be a relational database, doesn't really matter. We just run some projection code that takes events and writes to a different model. If you use that framework Martin again, just to show you what a projection could look like, now this is a single stream projection, meaning that we're only gonna get events from a single entity for one target entity in the read model. You also have multi-stream projections. Those are a little bit more complex, but not that much. Now what's happening here? Like we're seeing that we're taking our streams and we're projecting into an open ticket entity. And that open ticket entity has a GUID identifier. And then we have a couple of events that we want to subscribe to. For instance, if we have a log ticket event right here, that is going to force us to create a new open ticket. So we take that log ticket, and this iEvent wrapper, for instance, gives us access to the stream ID because we didn't put the stream IDs in there, right? And we just say, okay, let's create a new open ticket and put some data in there, right? And then if we get a resolution selected event, then we apply that to our new target entity. And that is just, we set the resolve to true. And then we have the delete event. That means that if for this entity we get a ticket closed, well, if we get that ticket closed, we just throw away the target record. So this makes sure that we have a table on the read side that only has our open tickets in it, and it just says whether they are still open or already resolved. This is a very, very simple example. Usually your projections are a little bit more complex than that. But again, quite easy to reason about how this code will function and what it will do on the read side of our system. What I love about this is that this has no side effects on our command side whatsoever. This also has no side effects for other projections. Like this runs in complete isolation versus the rest of your system. So you can take this out and take a look at what it does, and you can change anything you like without any problem. Now, domain-driven design gets drawn into this as well. And domain-driven design does what it says it does. We have our business domain that determines the way that we do our architecture and our code. Now, if you're familiar with the DDD community, you will often see people standing around the wall and putting up post-its. If you've ever met Alberto Brandolini, you've heard about event storming, which is a way to model business processes in post-its before you go and code them to understand what the business does. You could also use event modeling. Now, the cool thing about these two systems is they both have a color-coded system for commands and events and projections and read models and all of that. And basically every post-it you have on your wall will become a class in your system if you use event sourcing. You remove another step of translation. You don't have to think about how am I going to put this into a normalized model. No, all of those post-its just become new classes that you write one-on-one, and then you remove that translation. It's what DDD is all about, right? This matches very, very, very well. So that's why these three things get mentioned together very, very often. And that's where the cool stuff starts to happen. We have the base concepts now, but event sourcing can do so much more than this. Because we're getting so much out of the box that was actually previously tricky to do with our normalized database. First thing being point-in-time recovery. We don't always have to replay that stream until the end. We can replay that stream until any point in time that we care about, and then we have the state of that entity at that time. That comes for free, right? We can play to there or to the end. It doesn't really matter. So does that mean that we get an audit log for free? There's a very common misconception about CQRS or event sourcing is that you get your audit logs for free. This is not true. We have to enrich our event stream with a bit of data to make it a fully compliant audit log. We need to enrich it with who did this, why did they do this, when did they do this, and what kind of other metadata do we have in the system, right? We want to know the user. We want to maybe know what command that user issued. And correlation ID is stuff like we got a call from another node in our system and we need to correlate the request so that we know how stuff flowed through it. We also need to correlate the command to the events, all that sort of stuff. If you add a command log to your system, that's usually the easiest way to make this work because there you store which user did what and then you do have your audit log, right? Not that hard to add. The one thing that's tricky and that people worry about when you start with this is versioning. Because we used to do this. Our business logic changes, our model changes, we write a SQL update script to modify our database, right? We add some columns, we remove some columns, we modify some data. Ideally, in an event source system, we don't want to do that anymore, right? We want to keep our events as they were generated. Because if we're changing them, we might lose that visibility on how they happened. And again, we don't have a time machine. So what are your strategies? Well, the easiest one is make sure that your events are backwards compatible. If you're modifying them over time, make sure that the old versions still deserialize correctly into the new version. Often very easy to do if you deal with nullable properties and default values and all that sort of stuff. Now, at some point, you're going to want to change your event in a way that's not compatible. Now, the first thing you should worry then is this still the same event? Because often, us developers, we have the tendency to put some stuff into that event that's already there, although it is a different business event. Maybe we split it into 2 or 3 events, and then we can keep our events backwards compatible, which would be great. And if that doesn't work, at some point, we're going to have to maybe write some code that upcasts old events into new ones, or we will have different versions that are all being processed by our aggregate. We can have 2 apply functions for 2 versions of the event. At some point, like some of these frameworks allow you to have new versions of the stream. So if you really need to break compatibility, you can preserve the old stream and then write a new one and make sure that the new one then has the new versions of your event and so on. But that's more advanced. You can do that stuff, but it gets a little bit out of the way. Don't want to put that in this talk. But there are ways to deal with that still. But this is something you will need to be aware of. Like make sure that your old stuff that is stored still works when you're dealing with it. Now, one of the cool things that we get is on the read side of our model, we can write new logic. We have a new business request and we want to generate an insight based on our existing events. Well, what we can do is we can just write that code and then let it run. It'll replay our entire stream for all eternity. And at the end, we will have an up-to-date read store. And this is something that used to be tricky when we were doing normalized databases, because when we wrote a new feature that would query data in a different way, we would have to write some scripts that generated and maybe did some guesswork to fill out the tables that we needed for that feature. That's gone. We just write the code that we would write in runtime that takes the existing events or the new ones, and that replays that and the behavior into our read store. And this has no side effects, so it's not going to break anything anyway. And the cool thing about this is if you change your projection logic for whatever reason, you just throw away the target table, rebuild it, and it will be based on the new logic. So that part of the system actually becomes very easy to manage. But it means that you're going to have to tune your projections somehow. And your projections are going to run in different modes. Now, the one that feels most natural to people who work with relational databases is, I want to have my projection 100% consistent with my command side. And that's great. If they are written to the same database, we can do it in the same transaction, there is no delay, that's great. But it's also slowing down your command processing. Typically, this is not what you want. Your default should be something else. You're going to have to live with eventual consistency between your write side and your read side. So that's what we call eventual projections. They are processed before querying, but they might have a little bit of delay. The cool thing is we're not slowing down our command processing. Our command processing only has to dump the events into the event store, and the rest happens in another thread or even in another process. And that's the advantage of doing that. We can also have projections that are queried so infrequently that we only want to do the processing at the moment that we get the query. That is what we call on-demand projections. We project the data when we get the query, we fetch the source events, and we replay it in memory. Only works in specific cases. You cannot do this for a projection that requires us to query all of the events, and because over time that will become prohibitively slow, right? Another thing, because when we were talking about prohibitively slow, at some point you might have entities that have very, very, very long event streams. Let's say a certain entity gets so many changes over time that you're talking about millions of events. Replaying that for the next command might become super slow. And that's where snapshotting comes in. So we can basically compute the state to a certain point in our stream and then save that state as an auxiliary process. We save it in a different table or in a different store. We save it as a snapshot, which means that on subsequent commands, we can fetch that snapshot first and then only play the events that were after, that were coming in after that snapshot. And this is how we deal with very, very long event stream entities. Also, there's a couple of design patterns that could come in handy, and you're gonna have to deal with some of this reasoning, but it will allow you so much flexibility. When you think about commands and events and state, we often, the thing that I talked about in my talk, this is stolen from Yves Goeleven. He's one of my fellow Belgian software architects. And he blogs and tweets and LinkedIn's about this stuff the whole time. And he says these are his fantastic 9. And it's basically there are ways to go from commands to other commands, or from events to other events, or from state to state, or anything between those things. And all of these have reasons for being in a more complex system. Now, the one that you typically have to deal with, and the one that I showed you the lifecycle for, was the one that, well, my mouse does not want to play along, is the one in the top middle, the aggregate root, right? That's just processing commands and spawning new events. When stuff gets more complex and we have to talk to multiple streams, we might have multiple streams that we have to deal with. We also might have external systems. All of this might be a long-running transaction over time that we have to come back to when different stuff happens. We talk about sagas. And sagas is something you find in a lot of event-based frameworks as well. You're going to store some data for the saga. You can do that event-sourced as well, if you like. And then when it comes to UI, there's a couple of very cool patterns that you can use as well. Because if we add one more component next to our command API and our query API, what we can basically do is if we load a new page, we can load through the query API the initial data. And the initial data is going to show a bunch of entities to the user. Now, our UI could subscribe to updates for those entities. So we add this middle event API, and that's going to be some pub sub based on an entity ID. So it just could subscribe to everything that it's currently showing. Which means that if new commands come in from the same user or any other user using the system, that is going to spawn new events, and those events are going to get published to the subscribed UIs. Which means that if we then run some update logic in the same way in our front end as we would do in the back end, we have a live refreshing UI, even based on commands that other users are doing, completely subscribed to this system. If you use a state management framework in your front end that does applying of events, Redux for instance, this fits all together super well, right? And you can have these very nice event-based UIs as well. So, there's so much more to talk about, but we're already like only 5 minutes out. So where do you go from here? Where do you start using this stuff? Because there's so much stuff you can learn. There are frameworks for most of the languages that you might possibly need. I'm mostly on the .NET ecosystem. I love a framework called Martin. Martin works extremely well. It's used in production all over the place. It is very well maintained and it's very flexible and does all of the things that you saw in this talk. It runs projections and all of that for you. If you're on the JVM, you could look at Axon Framework. If you're on TypeScript, you could look at Emmet. On Python, there is some event sourcing packages you can use. Current is what used to be called Event Store, but is now called Current. It's its own database engine, but it has multi-language APIs that you can use. And there's a new kid on the block called Event Sourcing DB, which is just the event store. It is not the full CQRS framework. It's written in Go, but it has clients in multiple languages. So you can use it from Java and .NET and all those things. So pick one of these if you want to start playing with it. I know that the first initial logic of setting up and I've made this mistake myself in the past, it seems very easy to roll your own event sourcing framework, and you can probably get it, like the basic functionality out of the way in about a day. But if you have to evolve it and performance tune it over time, it becomes very complex. And I always love to focus on building business functionality and not the framework that I'm using. So I've switched to Martin most of the time to do my stuff. But pick whatever floats your boat. Pick something if you go to production. It'll be much easier to manage and evolve. And then the most important question, when would you want to do this? Well, if you get more familiar with this, it becomes a very natural way to think about modeling entities, and it becomes a very natural way to think about software. If you can get to the point where you're talking to your business people in terms of commands and events when you're modeling the business processes, then this is by far the easiest way to translate those conversations into code. Because all of the concepts will map between the way that you talk to your business people and the way that you write it in code. And that for me is where the big win is. But that requires the humans to be involved first. It's always a human problem. It's never a technical problem. We all know this, right? So if you want to know more about this, I'm on Blue Sky and on LinkedIn. I make some courses about this stuff on Dome Train, so feel free to go and look at those. I'll be around the conference today and tomorrow. And as I said, we will be playing music tomorrow night. I hope you have a fantastic rest of your build stuff. I'll stick around here for a little bit for some questions. The rest of you who don't have questions can go and grab some coffee.